Thank you, everyone, and good evening and welcome to this professorial inaugural lecture for Professor Sarah Boulton here at the University of Plymouth. It's great to see so many faces here tonight, and for those who don't know me, I'm Professor Chris Fogwell, the Executive Dean of Science and Engineering, and it's wonderful to see so many of you here tonight. Welcome to you in the room, but also welcome to you online as well. Let's say it is a hybrid event, so please feel free to put questions in the Slido if you're online. These events are a real celebration in any academic's career, marking a transition from an emerging expert in research and education to being a recognised international authority in one chosen field. It's a long journey. And as we'll hear today, a journey on which there are no shortcuts. From my perspective, as Dean of the Faculty, events like this are an absolute highlight of the year, and the opportunity to listen and learn from academic leaders like Sarah is such a privilege and actually the best part of my job. A professorial inaugural lecture provides an opportunity for both reflection and for perspective on this journey. It's a valuable opportunity to look forward to the next exciting chapter of one's career. It also provides a unique opportunity for many of us non-specialists to learn about Sarah's research and what motivates her. So the challenge for Sarah tonight is to give us a presentation that will communicate to us all, both the experts in the room and each of us who might lack the detailed understanding of neotectonics and geohazards, but also are really interested in what Sarah has to talk about and what makes her tick. So, at the end of the evening, you get to judge how well she's done. So no pressure at all, Sarah. Please do enjoy the talk. Inaugural lectures are open to the public deliberately, and hopefully we'll all learn something new from what's driven Sarah's career to date, her research ambitions, and why they are crucial to society. We'll also learn a little bit about her commitment to driving diversity in geosciences and STEM, which is really important today. Now I'm going to pass over to Professor John Shaw, Sarah's head of school, to give us a detailed introduction to Professor Sarah Boulton. Thank you.
Thanks, Chris. Cheers. Good evening, ladies and gentlemen. Welcome. I'd like to add my welcome to that of Chris. On behalf of the School of Geography, Earth and Environmental Sciences, of which it's my privilege to be the head. Now, there are many, many great things about my job, celebrating our students' successes, but also celebrating those successes of our colleagues. And those successes are recognised in different ways, from publication of papers to great lectures to research grant awards, and then in aggregate through their promotions. And tonight, of course, we're celebrating the promotion to Professor of Professor Sarah Boulton. Now, it's a particular pleasure for me to be here this evening to celebrate the promotion of Sarah as a long-standing and very valued colleague who makes a really wide-ranging contribution across all aspects of the school and the wider university. And Sarah and I first met in 1999, 2000. It was 2000. No, 2006. 2006. You can tell I'm a geographer, not a mathematician, so that's good. And Sarah had moved down from Edinburgh to take up a fixed-term lectureship here at the university. And I had come down from Aberdeen to interview for a job here at the university. So we were kind of swapping notes about that. And it subsequently came to my attention that in her interview, Sarah told the panel that she had every intention of being a professor within 20 years. And I can do the maths of 2006 to 2025 is 19, so congratulations on achieving that particular goal. Now, before Sarah was in Edinburgh, she'd done an integrated master's degree at UCL and was always interested in science as a child, I understand, and you went on holiday to lots of places with wonderful landscapes like the Scottish Highlands. So I suppose putting those two things together, it's neither a surprise that Sarah became a geologist and went to Edinburgh. for her PhD, and her PhD was on tectonic and sedimentary evolution in Turkey, and developed this theme with satellite data through the first part of her career. And satellite data is a relatively cheap way of getting lots of information, but it's a bit detached. And when Sarah was on a fellowship in New Zealand, in the Victoria University of Wellington, she experienced an actual earthquake. And there's a coincidence here, because on Tuesday there was an earthquake in the South Island of New Zealand, and one of the commentators, the academic commentators who'd been asked to make a presentation about this to the local media, was Sarah Boulton. Also, no relation, but also spelt exactly the same way, B-O-U-L-T-O-N. So, and she was also from Victoria University of Wellington, so there you go. But that experience of having an actual earthquake experience led to Sarah's shift in focus to co-seismic activity. So unstable landscapes caused by earthquakes can be every bit as dangerous as the original event itself. And Sarah's elaborated on this theme with local and global colleagues, and her current focus is on her excess project, which is funding of around about £1 million from the Natural Environment Research Council, which she is the principal investigator on. Now, Chris mentioned about Sarah's work in getting a much more wide participation in STEM subjects, and Sarah co-founded with Dr. Jodie Fisher Girls into Geoscience. There's another Antipodean connection there, actually, because as we speak, Jodie's on a plane to Perth to take part in a field trip. And the aim, and I'm quoting from Sarah here, is to encourage more girls and young women to study geoscience and adopt it as a career. Well, by any measure, that's been a huge success. More than 1,000 girls and young women have come to Plymouth to be in Girls into Geoscience events, and there's been at least another 1,000 who have gone to sister events elsewhere. And we're very, very proud to say that 50% of our intake into our geology programs is female. So many congratulations on that. I know you'll be hearing more about that soon. So, Sarah, many congratulations. I'm going to get out of the way because people have come to hear you speak. So welcome to the stage.
Thank you very much to both of you for that fantastic introduction. I don't quite know how to follow that on, actually, but I will. So I'm going to pick up actually on a lot of the themes that John has mentioned and give a little bit more depth to those. So if I switch to my title slide, I'd like you to take a few minutes to have a look at this. This is a hazardous landscape, perhaps something that we get to do with our students is, what do you see? So if you get your phones out, if you have no earth science training whatsoever, then click on the link on the right. And if you are an earth scientist, so you have a physical geography, geology background, click on the link on the, no, left and right, wrong way around. And it should take you to a little poll to put 3 words of what you can see in this beautiful landscape. So this is somewhere I visited in Colorado in the United States at a conference a few years ago. And one of the things we do as earth scientists is learn to read a landscape. This is a blessing because we can uncover information about the forces that have shaped the landscape at the present and in the past. But it's also a curse because when we watch films, we tend to think, oh, that's some nice geology, and maybe get a little bit distracted from what might be actually happening. So hopefully you can take another glance at this nice landscape and continue putting some 3 words in. I've tried to put myself in the mind's eye of someone without a degree. So I think maybe people might come up with words like this. Maybe you think that looks like a nice walk, the empty, isolated. Oh, it might be a bit fun driving, flat, pretty, maybe a bit boring, I don't know. Hopefully you've had a chance to put it in. So if we just switch to the Menti, we'll see what the non-earth scientists in the room perhaps think. Oh, okay, lovely. Oh yes, a road, mountains, hills. Oh, flat bits. Oh, someone, yeah, vegetation, lovely dirt. Actually, I wasn't far off, was I? I've got a lot of the words that people have got there. Hilly, Barren, yeah. Walking, yes, yeah. I think it looks like a nice place to go for a walk. Excellent, fantastic. But fairly generic on the whole. Whereas if we go back to the slide, and we put our geological specs on and shift our focus, then what I see, and probably what the earth scientists in the sea, is something slightly different. I can see the road, of course, good access. And there's not a lot of pesky vegetation here to get in the way of the geology. There's probably something called an alluvial fan. This is a cone of sediment deposited at the base of a channel in the mountains. We can see that the mountain front itself has these nice triangular shapes. These are called triangular facets and are really characteristic of terrain shaped by active faulting. There's some nice incised river valleys running down between them that we might call wine glass valleys. So then I can start to put some interpretation on those observations of an area of uplift and thinking that this is an active fault. And then I might start thinking about how active is it? When was the last earthquake? What was the size of the earthquake? So that's what I see. What do other people see? So if we switch the Menti for the scientists, well, okay. Mountains, landslides, it's actually quite similar, isn't it, to the other one? This is the interesting thing with a live experiment, online and in person. But yeah, break of slope, that's good. Faults, sediment, flash floods, grassland, floodplain. Yeah, so a lot of those things. So you can see that becoming an earth scientist, we start to see things in a different way. And we start to look at landscapes in a very different way. So hopefully that was just a nice little kind of icebreaker to get you in the mood. But I wanted to talk about a few things today. So what was my journey from viewing the world as this very nice landscape, but not much going on, to something more like this? How did I get to the point of interpretation? So as John said, I went to UCL. Choosing to do geoscience was, like for many people, you know, it's a big decision going to university, but there were a number of things that drew me. First of all, look how cool it is. I mean, it is a beautiful university. It's in London. I thought, yes, I could see myself here. Also, I really wanted to do a science that combined different sciences. I didn't want to just be a chemist or just a physicist or just a biologist. What drew me to earth sciences was that combination that we get to use biology, chemistry, physics, geography, maths to study the world around us, and that really appealed to me. So I went to UCL. I had 4 fantastic years there. I did some really fun field trips. So on the top left is the BTICS field trip. John Platt, some people might know, Mike Kaminsky. I'm hidden in here. I then did my mapping project in northern Spain, close to the Picos de Europa, me and my mapping colleagues. In my 4th year, we went to Din Yaban, and that's the famous Ammonite wall that I'm sure some of you have been there multiple times since. Most of my photos from that trip, though, involved Kevin Pickering, who became my MSci supervisor, with some sort of beverage in his hand, either coffee or alcohol. I'm not sure how many rocks we actually studied, but it was a great trip. And it really fired up my passion for science, and I wanted to take it further. I'd always had an idea, even when I started university, that I'd like to do a PhD. I wanted to go into research. I could see that as my future. But of course, when you start, you don't know if that will be the case. But I was lucky enough, I got a PhD position up at Edinburgh, and this is the Grant Institute of Geology in the King's Buildings. And we did lots of walking, had a really great time. Obviously, the most important part of going up to Edinburgh was doing my PhD, working with Professor Alistair Robertson on the geology of the Hatay Graben in southern Turkey. And this is the Hatay Graben here. It was a really amazing experience, and I learned a huge amount. I also got to travel. I got to go through into Syria, and I'm sure that a lot of this doesn't exist anymore. This is Palmyra in the desert, and it really was very formative, both scientifically, but also being able to see cultures and places that I hadn't seen before. And then subsequently, as John said, I got a position here at Plymouth. I really was very grateful, and it was Tony and Mark were instrumental in that. And I thought about putting embarrassing photos of them up, but I resisted. And they knew Alistair, they still know Alistair, and you know, it was really great to come down here. But coming to Plymouth made me think about what was I going to study. I could see that maybe staying on the basin analysis route wasn't quite what I wanted to do. And I started thinking about landscapes and hazardous landscapes and what they can tell us about Earth processes. So let's take a step back from that and just cover some basics, because I know not everybody in the room is an Earth scientist. So let's think about plate tectonics. So we live on an amazing planet. It really is unique as far as we can tell, because we have plate tectonics. So we have a core, solid and liquid, that are moving and generating magnetic fields that protect the really thin, hard outer crust. And between the core and the crust, we have this solid mantle. Even though it's solid, it is moving over geological timescales and driving the motion of the tectonic plates on top of it. So we've got mid-ocean ridges where new oceanic crust is forming, plates moving apart. Then we have subduction zones where that material is being returned into the mantle. We have strike-slip faults where material is just moving past. And this dynamic Earth is really unique. But that dynamism creates very big forces, big stresses. And those stresses in the deep Earth are ductile. They create folds. They kind of are soft and malleable. But near the Earth's crust, because it is cold and brittle, that creates breaks, ruptures in the Earth's surface that are faults. And that's what we're really interested in. Well, that's what I'm interested in. And we can split different types of faults. We can split faults into different types. So we've got reverse faults, where parts of the Earth's crust are coming together in areas of collision or compression, such as subduction zones or mountain ranges, where we can force one part of the Earth's crust over another and result in a net shortening. And then we've got the opposite, where the Earth's crust is being pulled apart, and we can create extension of the Earth's crust, like that. Now, you'll see that they're moving and the word earthquake's flashing up. And that's because the energy released when that crust is broken is felt as an earthquake. So an earthquake is the energy release. And it's really amazing when we look at where earthquakes are appearing around the world, because they're mapping out the edges of the plate boundaries. So this is where those tectonic stresses, those forces, are the greatest, and that stress is building up. And every day around the world, there are literally hundreds, if not thousands, of earthquakes around the plate boundaries. So I pulled this off last Friday when I was just putting the finishing touches. You can go online and look at the jumbo seismic monitor, and it will show you where earthquakes have occurred today, the day before, in the last 2 weeks, and over the last 5 years. And we can see that all the purple spots are really picking out those plate boundaries around the world. Last Friday, there hadn't been very many big earthquakes, actually. I think the biggest one on there is about a magnitude 6. So a fairly quiet day on planet Earth. But they're happening all the time. Now, of course, the problem with earthquakes is that they're very interesting, but they can be very damaging. And so we need to understand the faults that are generating those earthquakes in order to create safer societies. So we can do that in a number of ways. The first way we can do it is just by looking at the active faults. And here's Zoe in front of a very active fault. And so in some places in the world, we can actually go and measure and see faults at the surface. And so that's really handy. And it's really important to be able to go to these active landscapes and measure this information, because the information on that fault is really important. So people have spent a lot of time generating these things called scaling relationships that relate the size of the earthquake, shown here as the moment magnitude, against various properties of faults, such as the rupture length or the rupture depth, for example. And so if we go to a certain area in the world and we discover an active fault, we can measure its length, we can use these kind of relationships built up from many decades of study to then estimate how big that earthquake might be. So if we've got a fault 100 kilometers in length and we go across, we can see that's going to give us a really large earthquake around about magnitude 7.5, 7.6. And so, of course, this is incredibly important for determining seismic hazard and being put into risk assessments for all sorts of critical infrastructure. And we have to remember it's not just the earthquake itself that's really important to understand and study. Earthquakes are just an initial effect. And it's increasingly recognized that the cascading hazards that occur subsequently can be just as devastating, if not more devastating, than the initial earthquake itself. And this is a nice diagram showing a kind of circular, sort of ammonite-esque cascading hazard where we have an earthquake, we then have a series of hill slope failures, i.e. landslides, that then cause problems in the downstream rivers over time, over decades and centuries. But this could equally show things like tsunamis, liquefaction, changes to hydrology. There are a whole range of effects that an earthquake has. And what this also doesn't show is the human effects. So not only are there environmental effects, but of course, we could add in things like epidemics in here, where that downstream water quality is affected, leading to disease and other problems. And so understanding a hazard is really important for a whole range of reasons. But what if we can't see a fault? What if there is no fault in the landscape? We can't measure it, we can't see it. They might not always be obvious. And there have been some big examples, such as the Christchurch earthquake in New Zealand, where people didn't know there was a fault there. Even in countries with long historical records, they might not be moving, they might not have ruptured recently, people might not know they're at risk. We might not have a good understanding of the secondary hazards, never mind the primary hazards. And therefore, we can't, as a scientist, transmit that knowledge to governments, engineers, planners in order to make places safer. So what do? Well, we can use a range of different things. So a bit of background information for the next couple of slides. One thing we can look at is long-term landscape change. And we can look at things called uplift. But we have to be a bit careful because uplift also works with erosion. And there's this really fantastic sort of equation, if you like, where surface uplift equals rock uplift minus exhumation. And so I've just kind of made a really simple PowerPoint animation to show that. So in the first one here, we've got rock uplift. So this is rock uplift going up. And you can see that it starts at a lower point and then goes up. And then erosion happens and it lowers the surface back down. And so the difference between the starting point and the top point here is the rock uplift. We then remove erosion, we erode it, we remove some material, and we're left still with a difference between the two, and that's the surface uplift. So in some places in the world, we can actually go and we can look at uplift, and we can use the uplift that we observe as a direct measure of faulting events in the past. And so this is what we've done in a couple of places, and myself and Ian Stewart, bit of a geology name drop there, we collated and had a student who actually kind of started this, and we took it on and showed that in the Mediterranean, there are these things called notches, known about for a very long time, but they are indicators of probably paleoseismic clustering. So they don't represent a single earthquake, but probably groups of earthquakes close together in time. So what do I mean by that? Well, this is a beautiful example of a notch. It's called a mushroom rock in sort of the Mediterranean vernacular. We've got a notch at sea level here forming at the present day through a combination of biological, physical and chemical erosion. And so it's a sea level marker. If we uplift that, we then move it out of that intertidal zone and we preserve it. And the difference between the inflection point at the present day and the higher one tells us about that uplift. And in some places such as Crete, I don't know if you can see this in the room because of the light, but there's a really strong notch around southwestern Crete at the highest point of 9 meters. And that formed in a single earthquake event in AD 365. But generally, we think they have to form with multiple events because the uplift's generally not quite so high. So we can use direct measurements of uplift, but they're pretty rare. So what I started thinking about with others was how we can use rivers as a proxy, as something else that we can measure to get information about uplift. And so rivers are really amazing because they're basically a major force in landscape evolution. They are transmitting changes of base level, so the sea, the lake that they might be draining to, through the landscape. And they're agents of sediment deposition as well. And so they're really dynamic. Most rivers will have this beautiful concave up profile, steep in the headwaters, shallow towards their base level. But that steepness can vary quite dramatically. And this, again, we've got this uplift and erosion type equation here. So where uplift is low and erosion is high, sort of in areas that are probably quite old, post-orogenic, then rivers over time will get less steep. The slope decreases, erosion decreases, until we bring this uplift U equals E into balance, and that's known as topographic steady state. However, they do the opposite when uplift is higher than erosion. And in this case, the slopes of the rivers increase over time, again until uplift equals erosion. And so we can say something broadly about the sort of tectonic regime of an area just by looking at how steep the rivers are. And a lot of people have done work on that and have linked things like uplift rate to river steepness. What I'm particularly interested in, though, and what I've spent a large part of my career looking at, is a more transient feature of rivers. So not all rivers will have a nice concave up river profile. If we have a case like this, and this is a nice block diagram, we've got an active fault here causing uplift on one side and what's known as the footwall, and we've got subsidence on the other side known as the hanging wall. And what can happen if the fault is much more active than the time scale of the river sort of adjustment is that we can generate areas of incision that are known as nick zones. And then we have a nick point, this little star, that is a point in the landscape separating an area of incision from an area that hasn't been incised. And so essentially we have a pulse of incision that works its way through the landscape through time. And we can see that as gorges and waterfalls in rivers. And we can also see it in the river profile as the development of a convex reach. So this is where the top of the river looks normal, and then it suddenly gets really, really steep. And so we can measure and extract that information from digital elevation models. And really, the sort of satellite age of low-cost satellite data and digital elevation models has really driven a lot of this research because you can extract large amounts of data very quickly at virtually no cost. So we can go and study these pulses of incision across active faults. And we can start to ask questions of it because this incisional wave embeds information about the tectonics of the area in the river channel. So if we know that rivers are responding in a certain way to active tectonics, can we then switch that around and use the geomorphology of those channels to gain information about the active tectonics of an area? And so that could be really useful because rivers are pretty much everywhere, but exposed faults are not everywhere. So if we can just go to a region, extract some rivers from it, and say something about the activity of the faults, then that is a really powerful tool for improving the seismic hazard awareness in particular areas. So we tried that, and the first place we tried that was the Hatay Graben. So this is my PhD field area, and so this was kind of really one of the latter things that came out of that project. So the Hatay Graben is right down here. It's the little dangly bit of Turkey that goes into Syria. And if I just take away the map, you can see that it sits in a really important tectonic area between a number of plate boundaries. The Dead Sea Fault Zone coming up and accommodating the difference in plate motion between Arabia and Africa. The Cyprus Arc, the plate boundary between Africa and Eurasia, or in particular the Anatolian microplate. Turkey is in fact its own little bit of tectonic plate. And then we have the North Anatolian Fault Zone and the East Anatolian Fault Zone that are key structural lineaments in the region. And so the Hatay Graben sits in this really dynamic, active plate tectonic boundary. But what was really interesting was when I started my PhD, most people had no idea or didn't really have much knowledge on whether the faults were active or not. And so one of the first things I did was actually compile a map. Probably, now I admit, not my finest work, but it was quite a long time ago. And what we showed was that there are active faults along the southwestern boundary of the structure, and that they are shown in red. What we got really excited about, though, was that the river profiles were clearly perturbed and had these fantastic nick points in. And so I've just shown one here. This is in fact the main river. This is the Asi River. It flows through the Graben, and it's a major river system in the Middle East. And it has a fantastic nick point here. So you can see that upstream of the nick point, very low relief river, downstream of the nick point, very high relief. And each of the rivers that drains into this sub-river across this boundary had nick points in. And so one of the first papers that I published that didn't include my PhD supervisor, there were two papers, both with Alex. I took the lead on one and Alex took the lead on the other. We looked at these rivers that were flowing across these normal faults. And why this was different was that people had looked at individual rivers before, looked at a river crossing a fault, but what we did was looked at multiple rivers crossing a single fault and using each of those rivers to see how the fault behavior changed along its length. And so there were two key outputs really from that work that were really exciting. The first one is this graph here. So this graph, let me talk you through it, shows the height of the profile convexity, i.e. the nick point, that area of incision, versus the distance along the fault from the northeast to the southwest. And what you can see is that there is a pattern here. It's not just a random arrangement of points. As we go along the fault, the height of the profile convexity or nick point gets bigger, and then it gets smaller again. And that's exactly the same pattern we would expect to see if we were looking at what the overall displacement or offset on that fault would be. Bigger in the middle, smaller at the ends. And so what we could say from this is that actually, even though the rivers are not on the fault, they're preserving the same kind of information. They are a record of the amount of offset on that fault. Because of various bits of information we had about the age of the sediments, we could then kind of make some estimates on what we thought was the timing of formation of these nick points, and therefore allowing us to plot this second graph, which is a nick point migration parameter. It's essentially a normalized rate. So how quickly are these nick points migrating through the river systems when you plot them against the rate of throw, or the slip rate, how fast that fault is moving. And what we can see is that there's a positive relationship. So this was really exciting, because what we demonstrated with this is that the bigger the nick point, the faster it is moving through that river system. And so the rivers are actually responding, and the landscape's responding quicker here than it is here, but these are smaller nick points. So overall, the landscape will probably adjust about the same time, but it's variable through quite a short area. Now, the eagle-eyed of you will notice that down here, at rates of less than 0.5 millimeter per year, the graph is quite well constrained, and we've actually got data from Alex's PhD field area as well as the Hatay. But in both areas, those rates of fault motion are fairly low and they're fairly similar. And there's only 2 points that are, well, 4 points that are from slightly higher rates, but they have the same slip rate. So at higher rates of slip, that graph is not particularly well constrained. And of course, that then means there could be an error in here. So what we wanted to do was go to another location and see if we could generate the same kind of relationship. So yes, we can infer fault activity, but a good scientist wants to check that in a couple of places. You don't want to just rely on one study. So that's when we went to the Geddesgraben, and I'm still working there today. It's a fantastic natural laboratory for looking at Earth surface processes and the intersection between active faults and landscape. So we've moved from here over to here, to the Geddes, and this work was started by Emiko Kent. She was a school-funded PhD student, and the first student I had as a director of studies. And then this is Cihat Altacek, who's been a long-term collaborator with me in Turkey. And so we went to the Geddes, and Emiko's job was to do something similar, but in this area. So first of all, we looked at the geology, and it's really cool. It's got a normal fault system, but we can't see it because the geology is really soft. So we know it's there, but we can't go and measure nice fault plains. And it's not limestone dominated. Most places in the Mediterranean you go is limestone everywhere from the Tethys. Alex's field area was, my PhD field area was. So no limestone, pretty much. So it's quaternary alluvium, conglomerates and sandstones, and metamorphic basement. And we know it has a history of recent fault activity. So this is the Roman city of Sardis, or what's left of it, really famous for gold. So apparently a center of gold production back in the day. And some history of recent earthquakes. So there was a magnitude 6.5 earthquake in 1969. So we know it's active, but not a lot of information on the faults because there's no surface exposure. But there are beautiful rivers. And so we could see that there were nick zones, and we could go and measure them. And this is what it looks like in the nick zone. This is classic Turkish weather where it's quite hazy, but amazing V-shaped valleys, bedrock rivers with sometimes up to 300 meters of incision from the very planar surface in some places. By contrast, outside the nick zones, either upstream or downstream, it looks completely different. You know, we don't have bedrock, we have various types of sediments, big, open, broad river valleys with large amounts of sediment load. And again, if we look at the river profiles that are draining across, we can take multiple rivers and we can plot and measure the height of those profiles along the riverfront. And we can use, again, geological information. We can extract large amounts of data, and we can say that these nick points are consistent with an increase in slip rates along the rangefront faults at around about 0.8 million years. So this allows us to do a whole bunch of things, and this was really exciting. So this was really cool from a hazard point of view, because what Emiko did was some perhaps more classic structural geology. She plotted, this is a bit simplified, but she plotted some cross sections of the faults, and using data that had been published from the surface and the subsurface could work out actually how much displacement, how big was the movement across these faults. And then we could use some satellite data, some digital elevation model data, and split the fault up into little boxes and work out the topographic relief in those boxes for the sedimentary rocks. So the relief is simply the elevation difference between the highest elevation and the lowest elevation. And what we found was that there was actually quite a good, geologically speaking, correlation between the throw on the faults as measured using the cross sections against the footwall relief, whether we use the cumulative throw adding up across multiple faults, or just taking the throw on the main graben boundary fault that's active at the present time. And so that's really cool, because these relationships then allow you to go from places where, so this, is based only in the eastern part of the graben where we have the seismic cross sections in order to do that. So it means we can then go from an area that's well constrained to all the rest of the graben that isn't well constrained, and use the mathematical relationships derived from this graph in order to work out the slip rate. And that had never been done before, and is a really key bit of information for the region. It also then, of course, allowed us to work out how fast the nick points we had identified were migrating through the system. So again, this is the same graph, just made a bit bigger. We've got the fault throw rate here at the bottom, the nick point parameter rate again. The black bits were the data from the Hatay graben, the grey ones from Italy, and then these blue ones are the data from the Geddes graben. And you can see that in general, these faults are moving much faster. The maximum throw rate is probably about 2 millimeters per year here, so really, really quick. And it continues that relationship. So we demonstrated that, yes, we could say how fast they're moving through, and we could demonstrate that the faster the throw rate, the faster that nick point migrates through the rivers. But there's, of course, some scatter there. And that scatter represents things like climate and lithology. And there's some of the questions that I've been working on in subsequent years. I had to give a little shout out to Morocco as well, because Morocco has been really important to my career. Again, we kind of did something similar there, but Morocco is really different. It's very dry for a start. You might think Turkey is quite dry. Morocco is way drier than Turkey, but it still has amazing gorges, and the rivers have nick points. And so we did something similar with Martin and Anne, and looked at the rivers that were crossing the South Atlas Fault to see if we could see similar patterns. And it was a little bit different in Morocco, but the take-home message was that we could see something like 1,000 meters of incision in some parts of the mountain range indicated by these nick points. And that correlates really nicely with a range of other data sets that had been published on using sediments that were deposited in the marine realm and had subsequently been uplifted. So that was all very well and good, but then a few things happened. John alluded to these. This is one he didn't allude to, but there was a big earthquake in Nepal, a magnitude 7.8 on the 25th of April, 2015. And in fact, my husband and I had just got back from trekking in Nepal about a week, 2 weeks beforehand. And people that we'd met on the trek were actually on their way to the Everest base camp at that time. And so that was a close call, but it was super interesting as an event, and has led, as you'll hear about, to a whole range of research, particularly because it generated lots of landslides. It's now thought to have generated more than 20,000 landslides in that earthquake. It obviously killed a lot of people very tragically, and has been very well studied. So again, digital technology has really been a key aspect of developing these data sets. So that was one thing that happened. Another thing that happened was I got a Leverhulme fellowship to spend 4 months in beautiful Wellington, New Zealand. And I was going to be working on learning how to do cosmogenic isotope and nuclide analysis with Kevin Norton at Victoria University. And it was really beautiful. I got there, had a lovely time, took photos like this. Went to the botanical gardens. The sharp-eyed of you will notice triangular facets on the hillside. This is the Wellington Fault. It runs straight through the middle of Wellington through the botanical garden. So I was sitting there having my cup of tea going, oh, wow, that's an active fault there. Whew. And little did I know, a few days later, I was in the 2016 Kaikoura earthquake. Again, a magnitude 7, really big event, 2 minutes of shaking. If you've ever been in an earthquake, you probably haven't been in a magnitude 7.8, and it is a long time, 2 minutes to be in an earthquake. And it was really significant. So the rupture was there, I was there. And it was really complicated. A lot of faults ruptured in the event. And so really interesting from a scientific point of view. From a personal point of view, what I don't think I realized before I'd been in that event was actually how many aftershocks there are. You can academically know that there are aftershocks after an earthquake, but feeling them every day over and over again is a very different thing. And there were something like 20,000 aftershocks to the Kaikoura earthquake. And in the first few days, you can see many of them were still magnitude 6 or 5 plus, so very, very easy to feel. There was also a range of environmental effects. This is Wellington Harbour suffered liquefaction and damage, very well publicised damage to railways, and of course, lots of landslides. And again, these have been subsequently mapped, and you can see all of the black dots on this map show the landslides that occurred as a result. So there were two earthquakes that happened. Also in 2015, there were 2 papers published that really got me thinking. The first one was by Rob Parker and others, looking at long-term preconditioning of slopes, again in New Zealand. And so what they proposed was that an older earthquake, the 1929 earthquake, shown in black, influenced the earthquake-triggered landslides that subsequently occurred in the yellow event in 1968. So they proposed that there was some sort of decadal weakening of material that had happened in one earthquake that was retained in the landscape and changed how the distribution of earthquakes happened, earthquake-induced landslides happened later. And that was really interesting because that implies that actually earthquakes can have a really long-term effect on landscape evolution. Another paper that also came out in 2015 was by Odin Mark and others, who looked at short-term preconditioning, what they called enhanced post-seismic landsliding. And they published this figure that is really interesting. So that we'll just look at the top one. They use these other examples as well, but Chi-Chi earthquake's the interesting one. So Chi-Chi earthquake happened in Taiwan in late 1999. I hope 2000, that's the earthquake here. And it caused an increase in the rate of landsliding in the subsequent years. But this was quite a short-term effect. You'll note that this black line finishes 5 years later. So this wasn't a decadal effect, this was very short-lived. And when they looked at the other examples, there was either no preconditioning or a very short amount of preconditioning. So this was really intriguing because on the one hand, some papers were saying that, one earthquake could cause damage to the landscape that would last decades and influence landsliding later on from another earthquake. And then this other paper was saying, yes, maybe differently, but you can have an earthquake and then it will really change the rate of landslides caused by precipitation in the coming years. So either way, really intriguing. And this is important because if we go back to the impact, this is some work from Hakan Tanyas and his group, then they plotted and looked at the number of earthquakes that generate landslides, most of them. And some other work has shown that, around about 70% of all the casualties that are caused by earthquakes are actually the result of secondary landslides. So they have a really big effect. So we got some funding and we were very lucky to appoint Josh to a NERC-funded NV studentship. And so Josh's work was really to look at this idea in Nepal following the 2015. So Josh had a really big study area, 45,000 kilometers squared, that covered the area impacted by the Gorkha earthquake, but also some areas that had experienced severe flooding. So sorry, Josh, but I got him to map something almost 13,000 landslides using 30-meter Landsat data, and this is his resulting data set. So that was a lot of work, but it was super interesting. And this is one of the key outputs from Josh's thesis. And this is very similar to that graph that Odin Mark produced. So the key bits I will highlight. So first of all, this is the normalized landsliding rate. And the key bit really is here. And these two lines indicate what a normal year would look like, the number of landslides that we would expect if nothing weird was going on. The other things to know are, we've got some stars to indicate earthquakes, and we've got some precipitation data down here as well. So if we look at this then, if we expect most landslides to fall in this range here, we can immediately see something odd is happening here, something odd is happening here, and something very odd is happening here. So these two events were outburst storms identified from the precipitation data. And we can see that these really strong localized events do raise for 1 year the number of landslides that are occurring. But they have no after effect. The next year, it's just normal. By contrast, this bit here is the Gorkha earthquake, 2015, and it shows that in the subsequent years, particularly the year later, that there is an increase in the rate of landsliding. The key thing just to emphasize here is that this data, these numbers are normalized by the rainfall data. Other people have done mapping and shown that there are increased numbers of landslides for multiple years, but that data has not been normalized against the rainfall. We've got to remember that if you've got a wetter year, you'll probably have more landslides anyway. So that's super cool. So we've confirmed that the Gorkha earthquake indeed showed this preconditioning effect. And then Josh also looked to see what other factors were influenced. And I can see what the time is, so I'll just highlight that these lines here are steeper and have bigger R² numbers than these ones. And so the key take-home point is that peak ground acceleration, the strength of the earthquake shaking, plus something called excess topography, which is a measure of areas of the landscape that are too steep. When you add the two things together, indicate areas of the landscape that are really, really susceptible to co-seismic landsliding. And it was on that basis that I kind of pitched a NERC grant to kind of develop a landscape evolution model to try and explore these ideas in more detail and to bring together different data sets to really test this idea of how preconditioning, how excess topography all come together to shape landscapes that are at risk of landslides and earthquakes. And really excited to have two fantastic early career researchers, Suridoy and Amy, on board as a postdoc and research assistant to drive that forward. That's in early days yet. It's with a bunch of other fantastic people from a number of UK and international institutions and industry. And so keep an eye out for some amazing results from that in the next few years. So that's mostly me done, but I wanted to say a few other words. I could have spoken about all sorts of things tonight because I'm interested in the way that landscapes interact with earth sciences. And I just wanted to do a big shout out to some of recent and current PhD students who are working on lots of exciting topics. Storm and Rima working on tsunamis and coastal hazards. Manu and Matt, so Manu's graduated, working on Western Turkey, and Matt, who's going to be taking on really my PhD to a certain extent, taking that on, using some of the techniques that Manu developed. Jesse, who worked in Morocco with Martin as a director of studies, and Dylan, who's going to be kind of taking that on in certain routes as well. So, I really want to emphasize that science is a team, and having a great team of people around you is really important. But it's also really important, and I wanted to end with a plug for Girls in Geoscience. If you know anybody, 17 to 18-year-old, who wants to come, we'll be running it again 7th, 8th of July this year. As John said, Jodie and I started this here 11 years ago. This will be the 12th event this year, because representation in science is so important. And so we started Girls into Geoscience. It's a 2-day outreach event that we hold here at Plymouth every year. We do a field trip on the first day. Field trips can be a really big barrier to people who've never been in the field before, especially to women. Where do you go to the loo? What happens if you're on your period? These are all things that we've really got to consider. So we try and show that it's not a big deal. We can deal with it. We then have a second day where we have some lectures from women working in industry. Every year, try and get people from different companies in to talk about their route, their pathway, and what they do. And then we have some really fantastic workshops so people can get hands-on, and obviously we have question and answers. So really, it's to break down barriers, give people role models, and show what a fantastic subject sciences is, which I hope I've also done this evening. So why did we start it? Well, this was one of the reasons we started it. At an open day, probably around about 2012, I guess, I was talking to an applicant, and she said her teacher told her that geology is not for girls. This was a teacher to a student in the 2010s. I was shocked that someone could hold that view in this day and age. So, and I had a right old moan with Jodie about it over a cup of coffee, and we were like, well, let's do something about it. The other thing was that I started here at Plymouth, and you perhaps noticed from the photos in undergrad, my undergrad cohort was pretty much, it had a really good balance of male and female students. As a PhD student, there were quite a lot of female students. I came here and I was a bit like, where are all the females? Because at the time, and I think it was about the same, I couldn't get the 2006 data, but the 2011 data that we could get, I think it was probably a bit worse in 2006, showed that Plymouth geology students were 24% female and 76% male, against a national, still pretty bad, but slightly better, 35% to 65%. Not good. Physical sciences are very challenging. However, over a decade on, just about, we have seen a complete shift in this, and this is fantastic. I would like to say that Girls into Geoscience is completely the only reason for this, but obviously it's not. We have some fantastic sister events in Scotland, in Wales, in Ireland. Ireland slightly shifted its focus, but still working very hard. We have Gig Junior in Leicester. There is obviously a whole range of reasons for this, but nationally, we have seen a massive change. That if we now look at the geology students nationally, it's 44% female and 1% other against 55% male. And if we look at UOP geology, this was 2022-23. I think John referenced this year. It's slightly better, but we haven't got the data nationally yet to compare. We've now got 40% female, 3% other, and 57% male. So we've really moved the dial here, and it's something that I'm super proud of. And the whole team that goes towards doing this, and this is not everybody, this is the ones that could make it, the VCs Award the other year, me and Jodie collecting the R.H. Worth Award in 2018 at the Geological Society, and again last year collecting the Curry Fund. And hopefully there'll be more awards to come. But one day it'd be nice not to run it, because we would have 50-50 and that would be it. But as we can see from other countries, very small changes can roll back progress very quickly. So that's probably a hope too far. Okay, I'm going to stop there. I just want to say thank you. Thank you to all of my colleagues, past, present, and probably future, in the UK and overseas, and to research students, past and present, to the undergrads as well. Always a pleasure. Always, learning something from them. And of course, to my friends, many of whom are also my colleagues, and of course my family, for all of the support over the years. So thank you very much, everybody.
Well, I'm sure there are plenty of questions indeed. Thank you, Sarah, for a fantastic lecture. Really, really enjoyed that. A real privilege to see all of your career there condensed into just under an hour. And of course, I mistakenly said your career was over 26 years earlier on. Yeah, indeed, much shorter than that. Anyway, I'm sure there are lots of questions. Please do send them in Slido if you're at home. If you'd like to ask a question here, then please do raise your hand and wait for a microphone. Largely on the basis that people at home won't be able to hear you ask the question if you don't have the microphone. So I've got, by the wonders of modern technology, some questions which have already arrived. And I'm going to start with a local one. Mm-hmm. Have you studied the sub-aerial desert deposits of the Permian in Devon?
Well, I mean, we did have a student a few years ago, Martin and I, but not really, no.
Okay, a quick answer then for the first question. Okay, so here's one that's slightly more involved then. How do we take account of all forms of geohazards to assess risk to infrastructure, or can we only be hazard specific?
It's a very good question and very topical. So the traditional approach has been to focus on a single hazard. It's often hard enough understanding one part of the system, never mind trying to look at multi-hazards. But that's definitely the way the subject's going. And Rima, who I mentioned, is looking at multi-hazard and risk in Indonesia. And increasingly, people are trying to integrate different hazards and thinking about that hazard cascade, because one thing does have an impact on another, and that's definitely the way that the future is going. But it's difficult because there are so many things to consider.
Okay, thank you on behalf of the person who asked that question. So another one here, and please do put your hand up in the room if you'd like to ask a question. I shall get to you very quickly. I'm sure, says this anonymous questioner, that this is one of the most tiring questions you get. But how precisely can we predict serious future incidents based on evidence of previous geological activity?
Yeah, I mean, can we predict a hazard, basically, is what they're asking. I guess it depends what that person means by an incident, because it really depends on what hazard you're thinking about. But no hazard is entirely predictable. So volcanoes are more sort of getting towards being predictable in some cases, but earthquakes really not. So most people prefer to think about forecasting. So if you think about a weather forecast, there's an element of uncertainty there. It might say that there's a chance of rain tomorrow, a 40% chance of rain. And I think that's where I see the hazard community improving over future years, is improving that forecasting for various hazards, that susceptibility. I think being able to say on this day at this time an earthquake will happen is never going to happen.
Okay, all right. Thank you very much for that. And in which case, What about, let's move to someone who's just about to start out in their career. So when you were a budding young scientist many, many years ago, looking back over your career, what advice would you give to someone who's a budding scientist now?
Wow, it's difficult, isn't it? Everybody's pathways are so different. I think a key one is to not give up, be resilient. There are lots of stumbling blocks on the way, but if you can see past them and keep your focus on what you want to do, you can achieve anything. But yeah, I think that's the key thing, really.
Wonderful. Thank you very much. Very good advice. And we've now got 2 hands that have gone up. So 3 indeed. So Gert at the back is going to ask a question first, and he does have a microphone.
Thank you. That was really interesting, Sarah. I'm not a geologist, but I'm a physical geographer. I learned a hell of a lot. I've got a technical question.
Okay.
Sounds like a non-technical question, but how do you date a nick point?
Well, dating the nick point itself is difficult, but you can do it. Some people have done it because you can date features in the landscape. You can date terraces. So the Earth's surface is being bombarded constantly by cosmic rays, and they cause changes in Earth materials and create cosmogenic nuclides. So what some people have done is actually date terraces, and then you can relate the movement of that nick point against specific terraces. What we've done is more sort of inferences. We've used dating of sedimentary strata that you can date for a variety of ways, using radiometric, cosmogenic, or other things, microfossils, etc., to date sediments. And then if sediments of the same age are offset, you've got piercing points. And so then you can infer the age of the fault and then know when that nick point started. So there's a variety of methods depending on what information is available.
There's a question for the gentleman there. Just as he's getting the microphone, I will read another question from Slido. And this is picking up on your advice for a budding scientist question.
Oh, yeah.
So I'm a girl currently in year 13. I've never studied geology before.
Yeah.
How do I know that I want to do geology? I don't believe how this has been worded. How do I know that I want to do geology and not just geography?
Oh, sorry to the geographers in the room. Well, first of all, you can come to Girls into Geoscience. No, I think that's a really valid thing. Geology is not taught a lot at school. It's kind of hidden in other science subjects. And I think that's one of the scary things about going and choosing your pathway in the future is going to university. There's a lot more subjects at university that are available than there are at college. But I would say if you enjoy different sciences, if you enjoy the physical parts of geography, the sort of surface processes, volcanoes, plate tectonics, earthquakes, those bits that are taught within physical geography at school, you'll probably enjoy geology, because at university level, we tend to take those cool bits and leave the quaternary to the geographers.
Absolutely. So geography has its uses. Gentleman in the middle there.
Thank you, Ian Emery. Actually, I did graduate from this place, 1984. Across the road, I think this was a car park. Anyway, so I graduated in engineering, so I have only an interest in this, but I did do some earthquake design for the dockyard. But my question really is about Campi Flegrei. Have you any concerns? There's quite a Brady-sizing going on there, and seem to be repeating earthquakes. And I think every 40,000 years, something really exciting happens, doesn't it?
Apparently, volcanism is not my area of expertise. One of my colleagues, Paul Cole, would be able to answer that much better. Yeah, it's very difficult. It is active at the moment, but my understanding is that it was equally, if not more active in the 1970s. A lot of people were evacuated at that time. So it's obviously something to watch and keep an eye on, but the Italian scientists have got huge amounts of monitoring. evacuation plans and things like that. So yeah, it's really hard to know. It's not my area of expertise, but active areas are always worth monitoring. And if you're going there, being aware of what is happening and where the kind of evacuation routes and what to do in an emergency.
There'll be another question from the room in just a second, but I'll segue with one from Zoom again, from a psychologist.
Ooh, yeah.
Geohazards shape human histories, but these days maybe human hazards shape Earth histories. So if the second thing is also true, how does this new reality or realization shape the future of Earth sciences?
Wow, that's yeah.
Crystal ball for that one. Right?
Yes, I think it's I don't know is the answer. I think it's really interesting, and perhaps colleague Simon would have some insights into that. Yeah, I mean, obviously we are increasingly urbanized, and perhaps that will change the way people experience hazards, but otherwise I'm not sure I'm qualified to know. Yeah.
Thank you very much for having a go at the question anyway. So what I'll do is just take a couple more questions because you've already been asked to be on the stage for an hour and 10 minutes. And I can imagine it's, as you're not tired by the questions,
no,
but you might be wanting a drink of wine.
Indeed.
So the lady at the back there.
Hi there. So my work pertains to climate security and looking at displaced people, migratory people. So my thoughts here was the nexus convergence point between geohazards, climate and weather on these people and the possibility for early warning systems. You spoke earlier about the impact. Do you know within your work, is there the lens of securitization looking at that human geography element of the impacts, or are there existing work or early warning systems in place already? Thank you. It's not my background.
Great question. Early warning systems are really difficult, and they are definitely a focus in parts of the world, such as the Himalayas, that get really big earthquakes. They have landslides every year. They can have extreme outburst floods. I think we're probably on the cusp of being able to do it, but it's that integration of real-time data is actually quite tricky. But there are definitely research grants that have been funded at home and abroad in recent years, looking at that. How can we take data to make people safer? And there's a whole range of different approaches different research groups are using, from sort of big data and AI to monitoring, physically having sensors in the ground to try and do that. I hope that I tend to work on slightly longer timescales, but I hope that answers your question.
Okay, we've got time for one last question for the evening. The gentleman here in the jumper, pass the microphone along there. Thank you very much.
Thank you very much. A wonderful lecture. I'm Chris Brown. I came here 25 years ago to work on the dockyard, and I have lived through several earthquakes, but this is something right out of my field and your field. One of the geohazards that really concerns me at the moment is a change of the magnetic nature of the Earth. I don't know whether this is way out of anybody here's thing, but I'm interested in your original illustration of the planet. Mm-hmm. And my question is, way outside this, but how big are the iron crystals in the core of the Earth, and do they have effect on the magnetism?
I'm going to direct you to Tony at the back for that one. I don't know. I don't know if anybody knows how big the actual crystals are. Yes, but I mean, Tony might be able to. That's way out of my field of expertise. No problem. But there is someone in the room who might be able to help you.
I deal with Earth magnetism, but not the core. But some seismic studies of the core have suggested that crystals of iron in the inner core could be on the scale of 12 kilometers in size.
Whoa!
So absolutely massive. But but they don't really affect the Earth's magnetic field. The Earth's field comes from the outer core, not the inner core.
Thank you. Lovely. Thank you, Tony. Thank you very much. Well, thank you, everybody, for coming today. We're really, really pleased that you were able to come and celebrate Sarah's professorial lecture with us and Sarah's magnificent achievements throughout her career so far. There will be many more to come.
Yes, it's just the beginning, not an end.
Absolutely. Yeah. And it's our privilege that she's been able to do these wonderful scientific advances here at the University of Plymouth. So many, many congratulations. And I'm sure everyone would like to join you outside for a celebration.
Well, thank you very much, everyone. Thank you for coming.